Okay, we have dulong-petit law. It's about specific heat. This law is about specific heat. According to this law, the specific heat of solid is constant, and its value is 24.9 joule per mole per Kelvin. This statement or this law is valid only if temperature is approaching to zero. Like for smaller temperature, this law is true. There are some solids which do not obey this law, but majority obey this law at small temperature. So this law is valid only for small temperature. So we are just here. I just explained the statement of this law, and we are not going into the detail of this law. So next we have heat capacity of an ideal gas. As we know that by increasing the temperature, the volume of gases also changes. Like if we increase the temperature is increased, then volume of gases also changes. So due to this change in volume, heat capacity of ideal gases is of two types. Number one, specific heat at constant volume, and number two, specific heat at constant pressure. At constant volume, the specific heat is represented by Cv, and at constant pressure, the specific heat is represented by Cp. So here we will calculate or we will define a relationship between this Cv and Cp. So the relationship between Cv and Cp, we will derive this relation. We normally have a relation which is Cp minus Cv is equal to R, and R is the general gas constant. Now we will prove this relation for ideal gas. For this we will start, we will assume that we have a gas cylinder which contain gas, and we supply heat Q to this system. Now this heat energy stored in this system is a kinetic energy, like heat energy stored in the form of kinetic energy of the gas molecule. Like once we give heat energy to this system, then this heat energy can be stored as a kinetic energy if the piston on this system is fixed. If the volume is constant. Fixed pistons mean the volume is constant. This is one way. If we give this heat energy to this system, then this piston will move up to this point. So we have a work done on the gas. This is another case. Can be used, this heat energy can be used to do work. On the gas, on the environment. So we will consider both these cases, like if we give heat energy by keeping the volume constant, then the heat energy stored is in the form of kinetic energy. If we supply this heat energy to this system, then the piston will move and a work is done on the system. So in the first case we have a constant volume case, in the second case we have a constant pressure case. So we will discuss both these cases. According to first law of thermodynamics, the change in internal energy is equal to the heat energy supplied to the system plus work done on the system. Now first we will consider the case of constant volume. At constant volume, the piston is fixed. If piston is fixed, there is no change in volume. So the work done, which is defined as minus P into dV, will be equal to 0 because this change in volume is 0. So the work done is also 0. This is, let's say, equation number 1 and this is equation 2. Now when the piston is fixed, we can say that when the piston is fixed, then the heat energy, the energy Q, is related to the temperature by the following relation. Q Q is equal to NC into delta T. But piston is fixed, volume is fixed, so we can say that Q is equal to NCV delta T, where CV is the specific heat at constant volume. Specific heat at constant volume. Let's say this is equation number 3. Now using equation 3 and 1, using equation 3 and 2 and equation 1, using equation 2 and 3 in equation 1, we have change in internal energy delta E internal will be equal to Q is NCV delta T plus work done is 0. So we have delta E internal, which is equal to NCV delta T. So we end this video here, and in the next video we will proceed from this equation. Thank you.